So hello everyone, thank you for joining our live meeting today. It is my pleasure to introduce Bing Song. She's a postdoctoral scientist with, from Columbia University with Matei Ciocarlie from the Robotics Manipulation and Mobility Lab. She previously got a PhD in control theory from Columbia University, and she's interested in iterative learning method, optimal control, repetitive control, and reinforcement learning for robotics. And today she will talk about what can robots learn, what can robot learning bring to control. Please go ahead.
Shall I share the screen right now? I think, let me try. Does it work?
Yes.
Okay. Oh, since this is like a virtual talk, I cannot see our faces or reactions. Please just like speak up whenever you have questions, or you can wait for the end. I'll just like keep going. So my topic today is, what can robot learning bring to control? One answer could be it can bring job opportunities for control researchers these days. But of course, that's not my topic. What I will focus on is the technical side, and what I am interested in is how we can use learning to expand the capability of control. Or even further, how can we integrate learning and control to build a human-like nervous system that leads to intelligent robots similar to biological creatures? So first, what is learning and what is control? By definition, they're different as day and night. Learning is like the acquisition of knowledge or some skills from data, and control is to direct the behavior of a system. But for us, for our daily lives and for like intellectual creators, learning and control are intertwined inseparably on many levels. In other words, for an intelligent robot, I think we should design a system that the learning and the control are organically intertwined in a hierarchical structure. The design of learning and the design of control affect each other on different levels, for each level in this hierarchical structure. Next, I will use an example to demonstrate this point. And the example I use is iterative learning control, which is my PhD work. So what is iterative learning control? Iterative learning control follows the spirit of human repetitively learning a motion. Now let's think about how people learn to dance. How do we learn a dance move? We repeat this dance move again and again and correct this motion again and again until we have muscle memory. And in principle, that's how ILC tried to do for a robot. So what is ILC? Iterative learning control learns by repetition in practice to track a desired finite time trajectory with high accuracies. There are a few bullets to understand this definition. First, it solves a trajectory tracking problem. That means this motion, this finite time motion, is predefined or pre-given. And it is offline learning. The commands for the next iteration is computed before the iteration starts. The commands are computed between those iterations. And the third is this learning part is used to compensate for model inaccuracies. That's because the goal for the ILC is to approach reproducibility level of the hardware, which means we can use a not accurate enough model, but we can achieve the tracking accuracy beyond the model given us. And some research application examples include surgical robots, quadrocopter, and vehicles. Next, we come to the math part. Like, I will use a linear example to briefly introduce how ILC works. And then I will use two examples to demonstrate like how learning and control design affect each other in ILC. First, this is a state space model of linear dynamics. And suppose we are given a desired trajectory YD that we want this linear dynamic system to track. And we can write the control commands and system output of the iteration J as uj and phi-j, two column vectors. The relationship between the control commands and the output can be written into this equation. Yj equals to p times uj plus the initial condition at the jth iteration. First is what the P matrix looks like. This P matrix is written as this. And the components in the P matrix, CB, CAB, C squared, B, are the Markov parameters for this linear dynamic system. And they're actually the impulse response for the linear dynamic system. This P matrix is the key part for our design. So now we have this relationship between the commands and the output. What we need to design is an ILC learning law. uj, the current commands for the current iteration, equals to the previous commands, uj minus 1, plus an L, a learning matrix, times the tracking error from the previous iteration, ej minus 1. ej minus 1 equals to yd minus yj minus 1, the tracking error. And we can write the error propagation across iterations. The tracking error for the current iteration equals to I minus PL times the tracking error from the previous iteration, which means as long as we can design an L that makes the singular values of I minus PL smaller than 1, the tracking error will decrease monotonically. And we don't need an accurate model we don't need an accurate enough model to design L. We could use a model, whatever given us, to design an L, but still make I minus PL being a contraction mapping, which means the singular values of I minus PL smaller than 1. And this P denotes the P of the real dynamics that we don't know in the world. And the L is the model we used in the ILC for design. Everything in ILC is based on this I minus PL, a contraction mapping. So a recap for ILC. To follow a predefined trajectory, ILC learns from data in the real world and adapts the control commands as a feed-forward signals. And by establishing a contraction mapping based on a not accurate model, we can make the learning process safely and efficiently, as the tracking error will decrease monotonically. And to demonstrate this concept, I implemented for a point mass in Mojoko. Here is an example. which I ask this point mass to draw a figure-8 trajectory. And the model used in ILC contained some errors. First is it doesn't know there's a friction on the surface. Second, it has some error in the point size, which means the point mass will be different. The density will be the same. And we use random initial control commands for the first iteration. Then we apply ILC for learning. It will adapt, change the commands for each iteration until this point mass can draw a figure-8. And the learning curve we use for ILC looks like this. We use the RMS error for each iteration to evaluate how the learning is doing. And now here is the example. For the first iteration, it's a random action. So the point mass cannot draw a figure-8. But after learning for several iterations, like in iteration 8, it starts to know how to learn. And now it can learn and it can figure out how to draw a figure-8. And this is the very basic concept of ILC, and the key to the design of ILC is to establish this contraction mapping. And next are my works in ILC, and I will show how control and learning design can affect each other in ILC. First example is a low-pass filter in control can destabilize learning. A brush up of why and when do we need a filter in control. So an object has different vibration modes, frequencies, but we usually include only the low frequencies, like we only include this in our model, but we ignore this in our model. And this not included high frequency motion called parasitic vibration modes. And we do not want to excite this high frequency response in our robots. So we add a filter to cut off any signals at high frequencies. And will the filter destroy the contraction mapping in ILC? And if we have a filter, the original I minus PL becomes I minus PFL, which F describes the filter. And unfortunately, a normal filter will destroy this contraction mapping. This is because there's a mismatch between the frequency-based filter design and its finite-time implementation. What is the mismatch? A brush up of how we design and implement a filter. First, we have a frequency choice, and we design the filter in the frequency domain. Like, what is the cutoff frequency? Above the cutoff frequency, we don't want those signals. And below the cutoff frequency, I want those part of signals to stay. After we design a filter in the frequency domain, we write it in a discrete model, as we can only implement discrete signals in the real world. And then we can write the frequency response for this discrete model, which is HZ, is of this form. And it's the corresponding frequency response that can be seen limited by the sampling process for our real world implementation. So let's see the finite time implementation of the filter. Now the filter only applied from time step beginning at 0 and ends at p-1. So it is a finite trajectory. And we can write this filtering process for the entire finite trajectory, starting from time step 0 to the end. And hence we have F here, which is also a topless matrix similar to the P matrix you have seen before, but the D, CB, and CAB are the state space matrices for the filter, not for the system to be controlled. This is the filter we are going to design. Then let's check the frequency response for this finite time implemented filter. We can write the discrete Fourier transform of this filter F, which is very similar to what we want, as this one in the bracket is the HZ before, but we have the mismatch of delta here. This is the mismatch I was talking about. The frequency-based filter design and the finite time implementation. And because of the mismatch, there's a couplings between different frequency. And this coupling will destabilize the learning of ILC. So how do I fix this problem? I found out that we can use a circulant matrix instead of topless matrix. We filled in the upper triangular with the Markov parameters again. And then the frequency response is exactly as what we designed as HZ. And for the, well, after this, I need to make it zero phase. So I filter it forwardly and then backwardly. So the final zero phase circulant filter will be this F times F transpose, if we want to describe it in math. Here's an example of how the filter works. The real dynamics is a third order system, and the model we use in ILC ignores the higher order mode. I mean the higher frequency vibration mode. And we want to track a desired trajectory looks like this on the left. If we use a zero phase filter, that's a normal one based on the topless matrix, which is a field from MATLAB. After a few iterations, the tracking error can be as high as 20. The desired trajectory is at 1 in the end of the, like around time 1. But if we use a circulant filter, we can have what we designed for ILC. That's the tracking of this trajectory with very high accuracy. So this is the example of circulant zero phase filter for ILC. A recap for this work is that a circulant zero phase filter for ILC can stabilize the ILC process. And it is a non-causal filter for offline learning. So I think it is not widely used in robotics because it's non-causal. We need this finite time implementation. That's the point when we want to use a circulant filter. And mathematically, the theoretical basis of this circulant filter is the relationship between frequency response, the p-topless matrix, and the circulant matrix. And this is the example that a classical control design can destabilize learning process in ILC. The next example is that I want to show learning can improve the performance that control can possibly achieve. So when we add a filter, like we filtered the unwanted high frequency response, but what if we want those high frequency response? What if we want the robot to move with a very high speed and complicated motion? That's the time we need those high frequency response, and we don't want to filter those signals out. But we still don't have a good model for that. Can we push the limit of control for that situation? That's the case. What if we want high tracking accuracy at high speed? What can we do in that situation? We can gradually increase the control rate and update models during learning. And the challenge here is that if we want to recover the state space model, which is the matrices A, B, and C, that means we need a lot of data. It becomes system identification, a very complicated problem. That's not the amount of data we want to use for learning. So instead of identifying the state space model A, B, and C, we can actually recover the P matrix in ILC. That means we want to recover the Markov parameters, but not the ABC itself. And how do I do that? I actually put an deadbeat observer inside of it. First, we have a state space model. We can write an n-step model like this, and M is the deadbeat observer, which we don't know like what the exact M is yet. But what we know is that there exists an M that can cancel this guy. Once we can cancel this guy, we have the relationship between the commands U and the sensor output Y, that we don't need to know the value of the state to recover the Markov parameters. What we can do, what we need to do is to use the control commands we give to the robot and sense the data to compute this guy and then recover the P matrix. So here is an example. Still, we have this third order system, and we ignore or we don't know a higher order like pole here. And we have a model in ILC like this. What we can do, like if we don't use this gradually increasing sampling rate method, the ILC learning curve will be like going down for the first few iterations, but because of the error in the model is too big, the contraction mapping will not hold, and the tracking error will goes up. It will like go down and up. But now what we do is that we update the model and update the sampling rate at the same time gradually. So the tracking error, what we learned, goes down, and then once we update the sampling rate, we want to excite more high frequency response. We see an increase in the tracking error, but we update up the model at the same time. The contraction mapping holds again, and then the tracking error decrease again, and updates the sampling rate. We see more high frequency response. Error goes up and go down, go up and go down. And we can do this process, repeat this process, and until it reaches the desired sampling rate. Here is an example from 20 Hertz to 40 Hertz. Okay.
Excuse me. So I'm wondering if I'm understanding this correctly. So when you are increasing the sampling frequency, are you doing that adaptively, or just following a kind of a curve or something?
As predefined is fixed, I just decrease the delta t by 0.001.
Oh, okay. So it's like a linear increasing of the frequency.
Yes, I mean, like, in terms of delta t, it's linear. When we do the frequency, it's 1 over.
Right, yeah, of course.
So it's a weird increasing way, but I didn't do much like in study in terms of like what is the best to increase the frequency. What I tried is keep using this linear decrease of delta t, but I do try different delta t's, and there's a range, a limitation that this method work for delta t. Like once we have very huge or large step size of delta t, the overshooting will grow like much larger. So how fast we increase will depends on like what the threshold of the tracking error we want.
I guess it's a case by case problem.
It is. It is very case by case problem, and also this is a very simple model. And when it is nonlinear dynamics, when we need to use linearized model, that could be chaotic and it needs tuning.
Got it. Thank you.
Sure. So a recap for this, what we call this adaptive ILC with a deadbeat observer, which is I use some knowledge from linear system identification, but we don't necessarily need to do the real identification, which needs lots of data. And still, the richness of data actually determines the convergence. And that's also why that when we have a big step size of delta t, we actually need more data. And when we try to get those data, the tracking error could be very large. This is the example, like how learning can expand what control can do. And all these two examples are based on the linear models. What we use in real life is that we can use linearized based model for ILC. Here is an example that I applied ILC based on a linearized model of a snake and try to produce snake gates. The purple snake is at iteration 0, which I still give like random initial control commands. And the yellow snake is around iteration 200. After it's learning the gate, I give it to. So this is to demonstrate ILC can work for nonlinear systems, but needs more tuning and careful calibration, I think. And if I am given better model.
If I can ask a question, how do you find the error for the snake scenario?
For ILC, we have the predefined motion. So that means I already designed the angle for each motor, like at each time step.
Okay.
So that's the joint value. And for each joint, like we have this, I suppose we have this center value of each joint.
So
and then we compute the RMS error between the Q desired minus Q at each joint.
But do you also take into account the translation or only the error in the joins?
How the snake works is very interesting, is that we need to control the rotation of each joint, and the translation of the snake is actually depends on the friction on the surface.
Okay. Okay.
Am I clear? Like, we don't actually control the how much it's
okay. So your error depends only on the angles of the snake.
exactly, and how we control, like how we design the angles of the joints, that will like depends on how much or how fast we want the snake to travel in what environment, like how much the friction on the surface is. So that's the part we control the translation.
Okay, thank you.
Mm-hmm. So back to the nonlinear dynamics. The snake is the case I use a linearized model, and if it's for some nonlinear dynamics that we have a better model, like an analytic model or feedback linearized model, I can do better for ILC. I can make it faster. And that's what I developed, a bilinear ILC, which use bilinearization. And in that case, a big difference is that I don't use contraction mapping, but fixed point iteration for bilinear. So the convergence, like, kind of not guaranteed as what is guaranteed in linearization by this contraction mapping. And for feedback linearization based ILC, everything still, like, the theory in the linear ILC still applies as long as the feedback linearized model holds. If we compare the learning rate, we have a better model, we have faster learning rate. So this is my work in learning control. And what I want to demonstrate here is how learning and control can affect each other in the design. And this is like, ILC actually solves a very different problem compared to the learning we always refer to these days. These days, whenever we say learning, it's always reinforcement learning. And if you remember the hierarchical structure I was talking about at the beginning, I would put ILC and reinforcement learning on different levels in that hierarchical structure, where I think ILC actually lies on the very bottom level, which I name it as the muscle memory level or a muscle level. And in this level, the purpose of learning is to learn a predefined motion unit. The motion unit is already given. And in robotics, I think we have this, like, I would say, definition of the motion unit named as the motor primitives. And RL will kick in to learn the sequence of those motor primitives, which I actually name it as a task level. After we use ILC to learn each primitive, we could use RL to learn the sequence of the primitives. Some example of primitives that I've seen are like in assembly task, a primitive can be defined as, like, it is like once we want to insert a pack into a hole, a primitive could be like in contact and move until next contact. Something like change the rotation angle by delta each step until it has 2-point contact. That means it's already like at the right direction, and then we can insert. And in manipulation task, a primitive could be like the change of position along x-axis by delta x for reposing. And those primitives are very specifically designed for a task, a working environment, and a type of robots. What I was wondering is that, do we have other options to define a motion unit? And now I just take the human learning process as my guidance again. I was taking ballet class before the pandemic, and my favorite teacher not only teaches me the position of my legs, my arms, my feet, but also she taught me which muscle should contract, which muscle should relax. Actually, she teaches me how to control. So then I asked, can we learn the sequence of control for robots? That is what I'm trying to do now. I'm trying to figure out if we can learn the sequence of key parameters for control synthesis instead of the primitives. What do I mean by the key parameters? For example, if we want to design an optimal controller, the key parameters can be the cost function. And if we want to design an impedance or admittance controller, the key parameter could be the time response. That is also on a case-by-case basis. And next, I will take an optimal control as an example to see, okay, we can use this to replace primitives. There are benefits and limits, of course, for when we compare this, I would call controller primitive versus the motion primitive, but it's doable. Specifically, the example I use here is iLQR, which is an optimal control method. What we want to do is, I want to show that we can use a cost function to describe a certain type of motion, which can be seen as a primitive. So researchers, as what I said, they use serpenoid curves to describe the angles at each joint for a snake robot that can define the motion of the snake gait. And what I do is that I found we can use iLQR automatically generate those gaits, which is quantitatively comparable to the old way, the serpenoid curves. Here are the examples. And this is the gait when I use the same cost function going forward to some point. For the snakes, the same snake in different environment. The first one is the environment on a surface, like what a snake always do on the ground. And the second one is like a ribbon eel. And the third one is similar to, I guess that's a salmon. And we can generate gaits using this same cost function across these different environments, which surprisingly to me that quantitatively it is very similar to some or to their biological counterparts. So that means if we use a cost function to describe a primitive, it can have the benefits that we just need one cost function for different environments, that we don't need to design different gates in different situations. And more than these basic gates, if we manipulate with the cost function, we can generate gates to avoid obstacles. And we can also generate gates have a sharp turn. Well, I didn't add the collision check for the snakes, so you can see like they curl itself at the beginning in the turning example. So this is the way that I want to demonstrate we can possibly use a cost function to describe a motion primitive. And the possible benefits are we can use the same cost function across different environments. We don't need to use the predefined movement patterns as we need before, and that means we don't need to hand tuning the parameters for the controllers corresponding to different moving gates for different environment. And what I claim here is that there's a different way other than motor primitives that we can slice the task. I'm not claiming like this cost function like primitive is better or worse than the normal primitives that we are using in robotics, as on a case-by-case basis, I guess. What I want to propose here is that we can use the cost space for iLQR as a possible reinforcement learning action space. And this reinforcement learning action space made of cost functions is actually orthogonal to the RL action space made of motor primitives. Like one primitive task may include several cost functions to finish. And one controller, the same cost function could be used to perform different motor primitives defined for a robotic task. And I think it is like similar to the way that we can use RL to choose different models, local models that we use in the planning. And the same local model can be used for different primitive tasks. And one primitive task might require several different local models to finish. So in the task level, I think we can have three different three domains that are actually orthogonal to each other. One is the motion primitive domain, that we can cut a task into pieces of motor primitives. Another domain is the controller domain, that we can use RL to choose controllers. And the third domain is the model domain, that we can also use RL to choose models. And they are like intertwined and affect each other in a complicated way. I think that's the hierarchical structure I am talking about, like how those learning and control are intertwined organically. And I'm very interested in is whether or not there exist some universal rules to build such a hierarchical structure, or define which part we want to use learning, which part we want to use control, and how to choose primitives, how to design the controllers, how to choose models. Like as human, how to provide the choices of models and controllers and primitives for IL learn to choose. I guess it requires like much creativity to build this hierarchical structure, on this task level that if we want to include or consider all the possible choices in all three domains. And this is the very far picture in the future. And what I'm working on is I'm starting my work in this direction, learning the sequence of key parameters for controller synthesis. What I am developing right now is an iLQR algorithm that I use RL algorithms to choose cost functions for iLQR to like perform a task. The RL I'm using now are like PPO and DQN. And the concept is use a set of cost functions as the action space for RL. And what I want to claim is that compared to end-to-end RL algorithm, I think this RL iLQR can achieve balance between sample efficiency and motion accuracy. And possibly, I think it can improve the robustness, providing that we will give a better or we will give a model for iLQR. And I'm running experiments on this now, so please stay tuned for my preprints. I hope it can come like in the next month, but I was very procrastinated in this year, so we will see. I think my efficiency is getting better and better. And beyond this task level, I think the next level is the critical thinking level. The difference between the task level and the critical thinking level, in my definition, is the dancers versus the what's the name? How do we pronounce that? The choreographer, that who will like choose or doing some reasoning or inference of a dance. So this is the part that requires the temporal logic. And how can we make robot to learn reasoning and inference? That is the direction that I'm very interested in, and see if we could like combine the work from different fields together and build like a hierarchical structure that could be analogous to human nervous system. So this is my talk. The takeaways are learning and control should be organically integrated in a hierarchical structure if we want to design a nervous system for robotics. And I think the bottom level example is a muscle memory level, and we can use ILC to learn the unit movements. And on the task level, I am trying to develop RL iLQR, and what I claim is that other than motor primitives, we may use RL to design controllers. We may use RL to choose models, and all those three directions are affecting each other too. And what I hope is one day we can make robot dancers dance like what human can do. And that's the end of my talk. Thank you.
Thank you.
Thank you for the nice talk.
Hear the thought?
It's very interesting.
Thank you. Let me end the show.
So I have a question on the cost function of the iLQR. So I'm not from the control side, but to my understanding, in a traditional way of doing generating motion primitives is to impose some trajectories in a state space, and then and then deploy a controller to drive the robot according to the trajectory.
Exactly. Yes.
Is that right? But
yeah.
How does the cost function work with iLQR to generate the gate?
Here is this. The cost function depicts the purpose of the primitive instead of the joint angles of a primitive. Like the purpose of this is to go forward. And a cost function could be a quadratic cost between the head position and some goal position ahead.
Mm-hmm.
And iLQR does is to minimize this cost function based on a model. It will figure out the joint angles for each time step.
I see. So instead of using iLQR, can we just use RL to do the same thing?
We can do that using RL. And the good thing for RL is that it doesn't require a model.
Right.
The bad side of RL is that the amount of data is needed. And one other good point for using optimal control other than RL is that if we are given a model, we don't need to worry about the transferability from simulation to the robot. As long as the model is we could try to make its robustness to the model errors in control. But for RL, it's model free. Once the data in the simulation, once the simulation itself is very different from the real world, the transferability could be a problem.
Right, but for certain tasks where the models are very difficult to get, for example, in dexterous manipulation tasks, right? You are manipulating a random object, and if you want to get a model online, then it's like a super difficult task, right? So
exactly.
In that case, you don't have a very accurate model. You can only have a rough approximation. Do you think iLQR will still perform better than RL in that case, in terms of reality gap, crossing the reality gap?
I actually have some simulation results from using iLQR for manipulation, which I found that we can use iLQR, but not for complicated or dexterous manipulation tasks, but for easy, simple ones. If we just want to grasp, iLQR can do that. If we just want to turn a gates, turning some objects, like a rotation to a few angles, that works. And what I think is that what I prefer is to also use a hierarchical structure. Still, RL is needed to deal with any unexpected motions from the object or any unknown motions from the object.
Mm-hmm.
But at the bottom, instead of doing an end-to-end RL, I am hoping that we can use something we could call it primitive, like iLQR, to control the local motion of one finger or the relative position of 3 fingers.
Right.
And then we can use RL to choose those primitives. Well, but it's very hard. What's currently has already done is to use synergies, in manipulation.
What do you mean by synergy?
A synergy could be closing the fingers, open the fingers.
Mm-hmm.
And it kind of limits the
degrees of freedom to control.
Well, not the degrees of the freedom, but you can think of it as a synergy as a basis function. And we have several basis functions, several synergies to kind of establish the possible motion when the finger hand can do. That means like if we only have a synergy closing and opening, then we control the three fingers at the same time. We don't have any like freedom of doing one finger closing and opening.
Right.
That's the definition of synergy. It's still kind of decrease the degree of freedom, but not in terms of like hardware.
Right.
It still have those
from the control point of view.
Yes, exactly.
Got it.
Mm-hmm.
Thank you. Are there any other questions?
So if nobody else has questions, I have a few questions. So thank you very much for the talk. This is very interesting. One thing that, well, let's start from the top, actually. So one of the things that I was curious about, so you're proposing this hierarchical
like
control, learning and control approach, which I think is great. I think that's the way to go. However, one of the issues that you, and this is kind of tied with some of the other questions, more technical questions that I have, but at high level, one of the issues with this is, especially for, let's say, a complex manipulation task, is that data or either the data that we have of trajectories is not necessarily given fragmented, is not segmented out so that we can learn, for instance, when you grab a cup, it does not tell you, oh, this part of the trajectory is just going to the cup and this part is just about grabbing and so on, or really focusing on even within the signals themselves. If you think about the entire configuration space, saying, oh, these three configurations are only about the motion to the cup, and this are about the fingers that will grab the cup once it's there, and so on, or opening them up while it is transitioning. So how do you see this part, which basically will need to be mapped to the hierarchical structure? How do you see this coming into play?
What I put here is only learning and control, and another part I think is a perception or modeling. So I would say like that will be three of them kind of integrated together, and how to use data to figure out which configuration it is current in. That will be like another big field, a big challenge, I think, which I'm not, I don't have much work in, so I don't put it inside of here, but modeling is for sure one essential part in terms of building any intelligent system.
Yeah,
Is that a question, or am I understand or miss the point?
No, it's definitely like constructing, let's say, models or including here perception. But even if you discard perception, let's just, we have trajectories and you have only, let's say, the most simple thing. So let's say you have two tasks, two in sequence, two primitives that you need to do in sequence, but you don't know when the transition between the two happens.
I see your point.
So how would you, I know that this is not something that you show, but how would you think about that? What is it that this can be put into your framework?
Right now, I don't consider that much between this, like the gap between the transitions, because in manipulation right now, I consider like quite aesthetic. So like when a primitive is defined as finished, like in a certain time, then we just ask the robot to finish the primitive as what the primitive is already defined, like maybe in seconds, in 10 seconds, try this. And after this primitive, the object is supposed to stay where it is. If it's a successful choice of primitive, then the transition between primitives doesn't have the mismatch in terms of like the configuration. That's currently what I'm doing, and RL is supposed to choose the correct sequence of primitives.
Yeah. So that's kind of because this can be a difficult thing also for RL, like especially with manipulation because of context. You have all this hybrid modes, these hybrid things that pop up, and that's where I'm thinking that might be difficult to predefine modes and predefine all this or model like hand is. So it'll be very interesting to explore. But it's very difficult. Nobody really does it in a way we are doing it. So it's not.
If you consider an easier task, then you have the primitives well defined. I think I read a paper. I forgot which group, but it is a paper to like flipping a long rod, and it defines, I think, like tens of primitives into 3 groups, like sliding along the surface, and the second type of primitive is like flipping a finger to the other side, and another I think is like related to rotation.
Okay, I see.
I feel like is in this field is working from both sides. Like one is like focus on more, like use more or leverage more from the robotics or control engineers, what we can do. Another is throw in just like data and try to get as much as data. And I think it should meet in between somewhere. And the structure finally, when these 2 methods meet each other, will be some hierarchical structure.
Yeah, I agree. It should be somewhere in the middle.
Yeah, but it is very hard. It is very hard.
I had a couple more technical questions if we have time. One is really about the cost function that you learn. So how do you parameterize the cost function there, or like, and because for instance, I would assume that you could potentially learn it as an IRL, inverse reinforcement learning problem, or did I miss something?
You didn't miss it. I just didn't include it. It's just like right now, what I'm using is predefined cost function. The parameters, the structure of the cost function are already designed by me. Right now, I'm using just a quadratic cost, like on some interest levels, could be velocity, could be position. And what like the principle I designed the cost functions is try to make it as easy and simple as possible, as generalized. Like I don't want to put this problem into like cost engineering for a task. So I want to design as simple as possible cost functions. And right now, I give the parameters right now. But what I hope is that I will leave RL to tune the parameters. But the function form of the cost is still given. Like if it's quadratic, it is quadratic. If it's a function of the speed velocity. It is this function. And what RL is changing is the weights. Is the weights of parameters in front of each input values.
Thank you. I think we're a little bit over, so maybe I will ask you the last question offline. If anybody else has a question, or if not, then we'll thank the speaker. Well, I guess there are no other questions, so thank you again for the nice talk.
Thank you.
Thank you.